Good evening, everyone. Welcome to our week 4 review session for business analytics. I hope you have had a good week so far. And on this Sunday, you will have to turn in the week 4 homework assignment. I would like to know which of the homework questions we have 2 for homework for week 4 have you found to be most challenging, and where have you found concepts and operations to be unclear?
Hey, Jerry, this is T.
Hi, T.
Hi, I hope you're having a good evening. So for me, I had a question regarding question 1.
Okay.
Give me 1 second. 1A. So I ran the regression analysis on that, and for age, I got a negative slope, and that just didn't make sense to me because I thought that the age should be, I don't know, it just didn't actually, I don't know if it was that one. I'm sorry. Sorry, it was for question D. Sorry about that. 1D, the slope for age is positive, and I thought it should be negative, meaning the older a house is, the lower the value would be.
Okay, great question. I will take a note on that, what the relationship should be between age and house price. Great question, thank you. What about other students? Where did you encounter questions and difficulties?
I'll be honest, I'm having trouble with the homework, so it'll be great if we just go over them.
Okay, so you have explored both questions in homework 4.
Yes.
Which parts did you find to be most challenging?
Hold on, let me look at it. Mostly it's on problem number 1, so hold on.
Okay, I encourage you to pull out your Excel file and also your report writing in Word document, and let me know where you encountered such problems. Thank you for pointing out to be problem 1. I can take a further look at it. How about other students?
Hey, Jerry.
Hi.
Quick question. So for 2G, problem 2, section G, toward the end, it is saying that why is the answer different from the one in part F? I thought it would be more intuitive to compare the answer with part D, because one is the curve linear, and the other one is using this piecewise linear. So is it meant to be comparing with part F? Is it correct?
Yes. So let me check and make sure we both understand what the question is asking for. So you were saying that for problem 2, you
2G.
were not so clear why 2G was under comparison with 2F?
Yeah.
Okay, we will go into it, but the question was not worded wrongly.
Okay, all right. Just want to make sure that this is not, this is what the professor meant to do.
Yes, because he prepared all the questions.
Okay.
And he's quite good at checking out all the details.
Okay. Right, there's nothing wrong. I just want to make sure that this is
no,
correctly.
It was as intended. It was for a particular understanding for some properties of multilinear regression models.
I see. Okay, thank you.
Okay, how about other students? Are you all good with the homework questions, or did you encounter problems in other parts?
I just wanted to clarify on 2E.
Okay, 2E.
Slope,
right.
The slopes and the model in that regard.
I see. Would you mind describing what you have done so far in 2E? I would like to know your approach.
I use the dummy variable 0 to indicate if the income the person is less than the median, and 1 if it's greater, and then using that as a regression analysis.
Okay.
And the slope depending on the income quantity. The slope basically would be a determinant based upon if the income was greater than 1, the median, or not.
Okay. I'm not sure whether you have captured all the required variables, but there should be 3 predictors in model part E. Each of you should check whether you have done, whether you have 3 predictors in a model for problem 2, part E. We will go into it. All right. Should I move on from problem 1? Or should I also collect a few other questions from you? All right. While you're looking at your Excel file and Word reports, I will go into some of my notes for our weekly review session. You will be able to find a link to my review session notes in Canvas modules and TA sessions. For week 4, let's see what we have learned so far. In week 4, we expanded from what we learned last week on simple linear regression model. Last week, we had only 1 predictor in the model. However, this week we added a few more predictors, so that's why it's called multiple linear regression. It is still linear because it's meant to be referring to that it's linear in parameters. You could check out this link if you want to do a plot of piecewise linear regression, where the slope of 2 segments of the regression model differs between each other. This YouTube video shows exactly what needs to be done in Excel to generate a plot with trend line that has different slopes. And in this week, we also need to do some data processing for regression. This is particularly useful for addressing some of the questions in our homework. One student asked about part E in problem 2. That's where we need to generate certain indicators as dummy variables for categorical variable. We will use the same technique in problem 1, part D, I believe. That's where we need to generate indicators for location of a house. So let's, well, now we will go to the principle where we need to follow, that we need to follow to generate certain indicators. Basically, we need to generate k-1 dummy variables corresponding to a categorical variable of k levels. And after that, we also need to pay attention to how to interpret coefficients in multiple linear regression models. A very good way to do so is to refer to the regression equation. It's nothing additional, but we need to add a few more predictors just based on the simple linear regression model equation we practiced last week. And I also provided some resources beyond the course that could help you understand more about multiple linear regression. I encourage you to read all of them and try to answer these questions. I don't think we will go into it, but if time allows, we can check out some of these questions. I also supplied resources where you can understand more about R squared. Particularly, there's a concept called adjusted R squared. You also find this reported in summary output of linear regression model. So it's slightly different than R squared because it It is adjusted for the number of predictors to ensure that the model is as parsimonious as possible. And there's also problems regarding multicollinearity and also variable selection and variable manipulation. I encourage you to check out these additional resources, but they are not really required for the homework questions. All right. However, what's required in homework questions is two parts. In problem 1, we build on what we learned, what we practiced last week about the relationship between house price and some predictors. In last week's question, we have only one predictor, that's the size or the square footage of a house. However, this week we added a few more predictors. That's age, the number of bedrooms, and the location. And one student asked particularly that the estimate for the age of a home was positive. However, she was expecting a negative estimate. Let's see what we need to do for these questions. First, we build a multiple linear regression model with square footage, age, and number of bedrooms. It does not involve the location. However, in part D, we do need to include the location. Let's see how they differ. Well, I'm showing my screen of the Excel file that I built upon for problem 1. Here, originally, in your sheet, you will find city, age of house, size of house, bedroom, number of bedrooms of the house, and the price of house. However, I generated a few indicators for the city where a house is in. I will explain how I did that later. However, let's see what the model in problem 1, part A tells us. This is the result I generated for problem 1, part A, without neighborhood indicators. So as you can see, in this model, the age had a negative estimate. So whereas the size has a positive estimate, and the bedroom also has a positive estimate. So I would like, we have a practice section now. Could one of you interpret what each of the coefficient means? Probably I will use 3 students. So, well, maybe 4. Let's start from the intercept. Could one of you tell me how you would interpret what the intercept means? Its estimate is about 137,000. All right, feel free to unmute yourself and let me know how you would interpret the intercept in this model. Or do you prefer a call out? I could refer to one of you.
Hey, Jerry, I can try.
Hi, Vivian. Great. Yeah, sure. Go ahead.
For the intercept, so in this model, with all things being the same, the price will be 137,000. With that, I don't know actually.
Oh, okay. But you made.
This is T. I have a question. Hi. Would the intercept be what the price would be if all the other variables were 0?
Yes, exactly. But Vivian also made a very good point that when interpreting that, we must use some restrictive interpretation, saying that by controlling for other things. I think the phrase she used was by holding everything else constant. By saying that, it means that the constant is any value that's observed in the data. For example, for age, it means when we set a specific age at any value between 4 and 25 years of the house. For example, this could be 4 or 25 or 24 or any value in between. We do the same for size in the bedroom. For size, it's any size we can specify between 1,500 square feet to 3,900 square feet. It's like that. So, but T made a good point that the intercept is describing a hypothetical value of a house price when every predictor takes the value of 0. It does not always make sense or carry a specific meaning. For example, we cannot really observe a house in reality with an age 0, size 0, and 0 number of bedrooms. But to build the relationship between these predictors and the dependent variable, that's the value of house, we do need to account for this intercept. However, when interpreting the model or making predictions, because the age and size and bedroom will not altogether take the value of 0, right? We need to take a value that's as observed in the range of the actual observation. So we won't really encounter this $137,000 prediction in our model. So how
could it be, Jerry? I'm just curious. I know we talked about that last time, where that intercept value may not make much sense. But could that be land? Is, you know, when you have the price of land, it doesn't have any structure on it. Oh,
I see. You mean you were saying that the intercept refers to some value because of the land, the size of land. No.
Okay.
No, it doesn't, because as what we practiced last time, the variables that were not accounted for in the model goes into the error term. It doesn't go into the intercept. So what's not captured in this model, for example, you provided a variable that's the size of the parcel, size of the land. It's not modeled in problem 1. We do not have data on the size of land. However, it could potentially affect the house, the house price, right? It will go into the error term. That's the difference between the predicted price and the observed price. It won't be totally captured in the intercept.
Okay, thank you. I got it.
All right. Oh, well, we just addressed another question. However, I would also like your answer about how you would interpret age. The estimate was negative 5,000 or 6,000, about that much.
I would interpret for every year that the age increases, in years, it has this much of a negative 5,000 effect, 60/80 on the selling price. So it's the effect per year of home price on the home price.
Oh, very good one. However, it's very important to add another term saying that by holding other predictors at a constant value. By that, it means for when we interpreting the effect of house age, we do need to do something about the house size and the number of bedrooms. So I provided a tentative template about the coefficient interpretation. Let me find out. It must be. Oh, well, it was back into here. I see. Some good template we can follow is like this. Given the estimated slope of, let's say, 6,000 or negative 6,000 for the year, or the number of years, or the age of house, the expected value of house price falls by $6,000 for every 1 year increase in house age, holding everything else constant. This part is very important, saying holding everything else constant in a multiple linear regression model, because we do have more than one predictors. That's where we do need to address what happens to the other the predictors when we try to describe the effect of one of them. All right. So with that,
sorry, Jerry. So I just want to make sure. So when you're running multiple regression models, you have to be aware of how you word, right? So like you're saying, holding constant is because there are other variables, right?
Exactly.
Okay. Okay. Thank you.
Yeah. So another interpretation is in this way. It'll be useful to interpret when we illustrate the effect of specific change from one value to another. We will see how it's helpful for addressing problems after part A and part A of problem 1. However, it's still very important to say holding everything else constant. Okay, let's move on. So with that, we need to predict a selling value for a house with specific size, with specific number of years, and number of bedrooms. So have you already done this part? How did you build a predicted value?
I can take a stab at it. Jerry, this is T.
Hi, T.
You're asking for 1B.
Yes, correct.
So based on the regression analysis, I did price equals the intercept, which is that 137,355, minus 5680 times the years, plus 159 times the square feet, plus 83,431 times the number of bedrooms.
Oh, wonderful. So T provided a good example how we calculate predicted price. This is nothing different than what we practiced last time when we had the context of a simple linear regression. It's just that we need to add a few more predictors. Remember that it's quite helpful to use a regression equation, right? So for example, this last model we just estimated give us a predicted, regression equation saying that the predicted price will equal to intercept plus this age, coef of age, right, times age. Then we need to add a coefficient of other variables, coefficient of size times size. We do the same for bedroom. So now let's put this concept in use. With this in mind, we simply need to calculate the predicted price using this using the regression equation by referring to the cells. So we start from the intercept. So with intercept, we plus the multiplication between the coefficient of age times age. Where is the age? It's this. So we do the same for the next variable, that's size of house. We also need to take a multiplication with between the coefficient and the observed value of the predictor. So we do the same for each of the predictor. Remember that because we are going to use the same formula for, oh, that's interesting. Use the same formula for each of the predictor, for each observation. So we should use absolute reference for the coefficients by using F4, but relative reference for the observed predictor values. So this is the predicted price. I would autofill each of them. So it gives us a predicted price for the model we built in part A. Then using this principle, we could calculate what happens to a house with this much of predictor value. So we simply supply the required value of the size of house, number of bedroom equals to 3, and the age of house was 10 years old. 10 years old, okay. All right, then simply we need to interpolate this value using exactly the same formula that we would calculate for a predicted price within the observed cases of houses. Any questions regarding how we calculate a predicted price for a specific case that's not observed in the acquired sample? Oh, great. Yeah, see, it's straightforward. It's nothing more than adding a few more predictors to the regression equation. Using the same technique, we could address the question in multiple linear regression, just as what we did last week for simple linear regression. All right. Then you'll be able to also do part C to calculate the difference between a case with between two levels of square footage. So I wonder what you have learned from part C. Any any observations from part C?
Jerry, what do you mean any observations? I think we just have to,
like reflection. What things you find interesting when you conduct part C?
Got it. I mean, there was, the other two variables were the same, right? The 3-bedroom, meaning the number of bedrooms and the age. So really the difference was square footage. And I think as expected, the house with more square footage was worth more because that variable is a positive and not a negative.
Oh, okay. Good point. So T just mentioned a specific property of linear regression model. When we talk about the effect of one variable, it has nothing to do with the other variables. That's because when we assess, that's because just like when we interpret the effects, we hold everything else constant. That also means when we assess the effect of a predictor on the dependent variable, house price here, the effect of house size has nothing to do with the number of bedroom or the number of years of age. So we do not need we do not really need to use information about the number of bedrooms or number of years of age to understand the effect of square footage. So that means if the square footage increased by 300, we simply need to times 300 by this coefficient to see how much the house price would be expected to increase when this happens. Any questions in this part? All right, now we learned another property of multiple linear regression. The effect of one predictor, for example, house size here, has nothing to do with age or bedroom. So that's why if we are asked about anything about changes in house size alone, see, there's no change in bedroom or age. We don't need to use any information regarding age or bedroom because they were not changed in the question, right? So we only need to use the coefficient that's where the predictor changes. All right, let's move on to part D, where we need to build indicators for the city. In this example, we have a city of 4 distinct levels. It means we have observed houses from 4 unique cities. For that, we could potentially build 4, at most 4 indicators. However, we only need 3 of them in predicting or estimating a model. Before that, let's review my notes on the categorical variable building. Categorical variable such as sex or city here in this case, we could first, well, in real data analysis projects, right? We could describe its descriptive statistics, usually using proportions, just like in frequency tables, because we do not have median mode or some other statistics that could apply to continuous variable. For categorical variable that only takes 2 values, however, we could estimate a mean that could potentially be meaningful. However, for any type of categorical variable, we could code them using a dummy variable of values either 0 or 1, and derive certain statistics from it. So in our case of city indicator, we have 4 different cities. So we need 3 dummy variables corresponding to a categorical variable for city of 4 levels. So when that happens, when all dummy variables equal 0, it indicates that the reference category. So this category that's seemingly missing from the dummy variable creation or coefficient estimates is used as the reference level for all other categories. So its information is not lost. We still use the information in modeling. And using a different reference category is arbitrary. It's just our preference or the researcher's choice. There's nothing correct or wrong by choosing a different reference category. We will notice very soon that this does not affect R squared. However, it does affect the coefficient estimates, but specifically to those estimates regarding this specific categorical variable that we built the dummy variables for. It does not affect coefficient estimates for other variables. However, this will result in different interpretation of the dummy variables that we just built. Well, let's put in the principles here into use. So speaking of that, I will hide it. Okay. As we just learned, for 4 cities, we built 3 city indicators. In this case, I chose Lake Forest as the reference. You could have chosen a different categorical variable. We will see what that will do. The dummy variable is nothing but a if-else statement. For a city that's Coco de Casa, we will assign a variable called Coco de Casa. Well, I shortened it to be Coto. So if the name of the city is Coto de Casa, the value will take 0. We will take 1 for this variable, otherwise 0. That's why you see I used an if-else statement here. I used the second variable for the second city in the for a second city, that's Rancho Santa Margarita. That's where this variable is built so that if the city name is Rancho Santa Margarita, then its value is 1, otherwise it's 0. By the same principle, we build another variable that's Mission Viejo. If the city's name is Mission Viejo, then we take a value of 1, otherwise 0. So using the same principle, we calculate 3 dummy variables. Any questions here? Did you build dummy variables in a similar way than what I did? Oh, great. Then let's move on. Using the 3 dummy variables that I just built, we could generate another multiple linear regression model in this part with neighborhood. In this case, I used Lake Forest as the reference. You notice that there are 3 new variables introduced in the coefficient table. That's the 3 new indicators I just built, Coto de Casa, Rancho Santa Margarita, and Mission Viejo. However, in this case, one of our students noticed that the age was estimated with a positive value. That means the point estimate of the coefficient of age is positive. So she was concerned whether it means that an older house somehow was predicted to be sold at higher price. So this is a reasonable concern. However, in future weeks, we will learn something about p-value. We notice that the p-value for age in this model is 0.63. A conventional threshold for a significant variable is 0.05. It's much larger than that. It's above 0.05. So we call that a non-significant predictor. And it means that although this estimate had a value that's not 0, but it's not significantly different from 0. So we could omit this predictor without significantly lowering the prediction power of our model. So we could treat the effect of age on house price as 0 according to this model. However, this model may not be perfect if we have additional data on other variables, or we have a good theory about what the relationship should be between age and household price. We could build a different model using even the same data. For example, I could hypothesize that the age effect is not linear. It could be a curve. It could show a parabola relationship. So that means I would introduce a different, one additional variable, that's the square of age. With that added to this 1, 2, 3, 4, 5, 6 predictors. So we have a 7 predictor model. The coefficient of age and square of age could be all different. So the age of the age of the house could show a different relationship because I add a different, one additional variable about age, that's square of age. But these are some more advanced technique. We don't have to practice them today. So are there any questions regarding how we could address part C, I believe, in part D already?
Jerry, so I'm hearing you say that in this case, it's fine the way that it is. Because I also ran a correlation of regression analysis, okay, and I didn't find anything that would make me want to remove that variable. And I think one of my peers, he removed the variable and it didn't make a difference either. It still was positive. So
what do you mean by remove a variable? Which variable did you remove?
Because for the age, Anderson, I think we thought there was like a multi-collinearity situation happening.
Right.
So we
okay.
Tried to, yeah, go for it.
So I actually, I tried it in both ways. I first removed, I think it's either, I think it was the size that I removed, and
you remove the size, okay, and see what happens to the coefficient about age, okay.
Right, and it was still positive, but however, later on, I did try to swap it around. So instead of it, I kept the size and I removed the bedrooms, and it actually turned out to remove that positive coefficient in the age.
Oh, okay, I see. So you did, you estimated another 2 models. In one of them, you removed the size. In the second of them, you removed the number of bedrooms, and you see different results. Yeah. This is as expected. Was it surprising to you?
No, I think, well, I was suspecting that there is a multicollinearity problem.
Okay. So could you describe briefly what you have learned about multicollinearity?
Some, like, before we go into interpreting the coefficient itself, you usually go to the graph first, and you also look at the variable that you have on your hands and see whether those slope make sense. And I think by the lecture, the professor did mention that whenever the variable with their corresponding coefficient doesn't make sense, there may be a multicollinearity issue. And
oh, I see. Okay.
Yes.
Yeah, he did have
Gary,
a good
essentially,
point.
like, there's a strong correlation between 2 variables and not like the actual independent variables, I think is what the lecture said.
Yeah.
Okay. Good point. So it's possible that this happens because of multicollinearity. It could also happen because of something else. It may not always because of multicollinearity. When the estimated sign of a coefficient is different than expected.
Oh, okay.
Yeah, I did provide some readings about multicollinearity. I encourage you to read some of them, or maybe all of them. One important practice is that we could test how strong the multicollinearity is by using a statistic called variance inflation factor. You could learn about them on Wikipedia. There's also a comment about it. There's something we could do about multicollinearity to reduce it when in certain situations. This situation is when we have higher order terms. For example, when we build polynomials, when we take squares or cubics of a variable plus the variable itself, or we have interactions between two variables or even many variables. However, if we do not have higher order terms, like this case we have at hand, we are not building interactions or polynomial terms, right? Doing this, centering variable, we will not reduce multicollinearity. So when multicollinearity happens, there's usually nothing we could do about it. So in practice, we center variables when we build polynomial or interaction terms. However, we are not doing that for homework questions. There's a good article or blog why we do so. There's also a academic article about multicollinearity and misleading statistical results if you want to see how this matters in academic research. All right. Oh man, I should move on by showing another model. This is a different model. Where I use quoted casa as the reference. Let's see, has any of you also done the same way? Did any of you choose quoted casa as the reference? Because it was listed as the first city due to the alphabetical ordering. All right, let's see what the similarity or difference are between these two versions of models by showing them side by side. On the left, we see a model using Lake Forest as the reference. On the right, I have Coda de Casa as the reference. These two models were built from the same set of data, except that the reference level of the city was different. For the second model, for the first model, I used these three variables as the predictor, plus age, size, and bedroom. So 6 predictors in total. However, in the second model, I used Coda de Casa as the reference level. That's where I also have 6 predictors, but one of them is different. So in the second model, I have these columns as the predictor. They are shown very specifically here. The name of variable for city are different in these two models. So let's see how the model estimation results are similar or different. We notice that multiple R, they are the same. Well, let me just reduce them so it's shown more easily. Okay. Multiple R is the same between these two. R squared is also the same. Adjusted R squared is also the same. So as the standard error in number of observations. You will also find that this ANOVA table is also exactly the same between these two models. So up to now, we know that if we used a different reference level for a categorical variable, then the predicting power of the model won't change because it will have the same R squared. However, if we go to the coefficient table, we notice that there are some difference. The intercept between these two models are different. So as the coefficient for the CT indicators. Remember, we built 0, 1 dummy variables for CT. However, if we move on to the continuous variables about age, size, and bedrooms of a house, we notice that these two models give exactly the same information. If you even move on to standard error, t-value, or p-values, these parts are also exactly the same. So it tells us that when changing the reference level for a categorical variable in regression model building, it only matters towards the intercept and the coefficient estimates about the categorical variable. It won't affect anything else, including the coefficients for other variables. Well, with that known, let's interpret the coefficient. Could one of you let me know what Rancho coefficient here means? It's estimated to be about, well, 300,000. And it's negative. Any volunteers? How would you interpret this coefficient here?
It's T. I'll take a stab at it.
Great.
I would interpret it that Rancho, that those homes are worth, you know, less 300,827. Like it's lower. Like, I guess, what am I trying to say? Like, it's one of the lower end home areas to buy because it's negative 300 versus the other ones are negative 240, negative 204.
Mm-hmm. So, were you comparing to these ones?
Yeah, but I guess if I'm just talking about that one variable, I would just interpret it as the base price of it is going to be negative 300,827 from whatever you're calculating for. So it's like a cheaper home compared to the other two, if I'm understanding correctly.
Okay. I don't think it's completely correct, though. I will show how. So how about other students? Would you interpret the coefficient in the same way than T or in a different way?
Honestly, I would go with her. I would interpret it the same way as she did, but obviously it's not correct, so.
Yep. Okay, I see. So it does seem that there's some difficulty in when we interpret the coefficient of a categorical variable. So during the interpretation, we've also followed the same idea as any other coefficient. That means we need to hold everything else constant. By fixing age, size, and bedroom at a constant value. This constant could be any value observed in the sample we have. When addressing a categorical variable coefficient, however, we are not comparing the coefficient to other coefficient of the dummy variable indicators. We are comparing the coefficient with 0, because here, notice what this variable of a Rancho stands for. It assesses the difference between the household, the house value in the city in the reference category to a city that's in a category the coefficient corresponds to. So here in this model, Coda de Casa was the reference level. So we are comparing every other city with Coda de Casa. That means when interpreting the coefficient, we also do the same thing. This coefficient about 300,000. What's the difference? Estimated difference when holding other variables constant. The difference between a house value in the city of Rancho Santa Margarita from 1 in the categorical variable, for 1 in the reference category, that's Cota de Casa. That means, for example, if a house with some house characteristics was worth, let's say, $500,000 in the city of Cota de Casa, a house with the same character in age, size, and bedroom would be worth less by $300,000. So it'd be value somewhere about $200,000. So we're comparing the coefficient stimulates us to compare a house in Rancho Santa Margarita to 1 in the reference category, Cota de Casa.
Got it. So Jerry,
any question?
With that thought process, then could we say for Mission, then a house at Mission, with the other things being constant compared to Cota de Casa, is always going to be $240,912 less, and then for Lake $204,000, $346,000 less.
Yeah, exactly. You did a great job. Yeah. Although I noticed that you use a word always, so this always pertains to prediction alone. So you there's a difference between the predicted value and observed value, right? It goes into the error term. So you're right in by using always saying that when making predictions, we do take this difference for each house in the prediction for these cities. It won't change. If we make another prediction about a house in Rancho Santa Margarita, we still use this coefficient to represent the difference between the value in the reference, that's Cota de Casa, and Rancho Santa Margarita. So great. All right, well, we are coming to the end of the review session, but maybe we could discuss something about problem 2 briefly, if you need any guidance. Right, I recall that in the beginning, one student wants some help in F and G, but it was written correctly. And one student wanted some help about part E. Have you encountered some other problems in problem 2?
So I have a question. Did you say question G or F and G was written incorrectly?
It's correct. Nothing wrong.
Oh, okay. I heard wrong.
Well, then let's make a quick review. For problem 2, we are, okay. I don't know what happens here. A very useful, potentially, suggestion is for doing any analysis before calculating descriptive statistics or building models. It's always good to plot the data. In this case, we have only 2 variables, life satisfaction as the dependent variable and income as the independent variable. So we could generate a scatter plot as shown here. I think the scatter plot was required in part A. Yes, it was. As the scatter plot shows, it could potentially review a parabola relationship between these two. That's why we could build a model with a squared term. And some students were curious how to generate square the value of a variable. So for such questions, I always I encourage you to use Google for certain operations. It's always very helpful if you're not familiar with certain calculation in Excel. Google always provide very good answers. So in this case, we simply use the caret symbol to represent power. So here it says we raise the income by the power of 2. Then with the generated square of income, we could build a model just like shown here. I call it a second order polynomial model. So that's where you see that the square of income as well as income were both included in the coefficient. And we have the estimated coefficient. Any questions in building a model with a squared term? All right. Now let's move on. With that, with the squared term added, we could use the same principle as what we practiced in the house price example to generate predicted value. I did it here. However, it's very important to notice the unit of measurement, measurements, so that the income is not interpreted wrongly. In the question, we need to predict how well the satisfaction of one with an income of 60,000, right? But here, because the income was assessed in thousands already, so we only need to put in 60 or 70. If you supply the value that's 60,000 here, we would times another 1,000, then it becomes 60 million. So notice the difference. I generated the predicted life satisfaction using the coefficient, using the coefficients and the required level of income, as in what we would do out of a regression equation. Any questions here to generate predicted value of a model with second order polynomial terms? Oh, great. See, it's nothing different than what we practiced in problem 1. It's simply a linear combination of coefficients and predictor values. However, in the next part, it might be challenging to some students where we need to build a dummy variable as well as an interaction. So last time in a different section of students, one student was particularly not sure why we need a interaction term at all, because he believed that all the effects as announced here was captured by a dummy variable plus the income itself already. So he did not use an intercept, interaction term. However, interaction term is actually required to address a question like this. Did you encounter similar questions? Do you understand why an interaction term is needed in part B? Okay, this interaction was expected because the specific way of the specific way of assessing the effect. Here we need to let the impact of income on life satisfaction depend on something. This something is which income a person belongs to. Notice that the impact of income on life satisfaction is quite different than the income directly. So because impact of income is assessed by the coefficient of income, it's not income itself. That's why we need the interaction term. This would be most easily illustrated in the estimated model itself. So let's see what happens in the model. In this model, I have 3 predictors: income itself, a dummy variable, and an intercept. The income was given in the original data sheet. However, I also built a dummy variable to represent whether a person was from a high income group. That means if a person is from high income group, then the value of the dummy variable is 1. Otherwise, it's 0. That's why I used also if-else function, just like how we built the indicators for city in the house price case. So here, as instructed, I used median as the splitter. For those with an income above the median, the value for the dummy is 1, otherwise 0. So as you see here, because all the income was already ordered from the smallest to the highest income, right? So you see that the first half of people, well, participants in the sample take value 0 in the dummy variable, whereas the second half takes value 1. Then we could build an interaction term. The interaction between income and dummy variable is nothing but the multiplication between them as income times the dummy variable. So because the first half of the participants had 0 as dummy variable, and when 0 times any value, it becomes 0, right? So that's why you see that for the first half of the interaction term, all the values were 0, whereas for the second half, we're multiplying income with 1. So that's why this interaction term takes value exactly as in income. So what it does when these 3 columns were used as predictors, this model tells us we had this model estimation results as shown here. So I provided the equation as here. So out of the summary output, we could write the regression equation. This is particularly useful for a model with the interaction and the dummy variable because this dummy and interaction has specific meaning and it differs between 2 groups. Let's see what I meant. So let's first build a regression equation for the low income group. For the low income group, remember that the dummy variable representing whether a person is from high income group, right? It takes value 0. At the same time, the interaction also takes a value of 0. So when we supply it to the regression equation, let me enlarge it so it shows more clearly. We could write the regression equation for the low income group in this way. First, we have the intercept, right? It does not differ, but we move on to the second term, income. We supply the slope for income times income. Then we do the same thing for the other terms. For dummy variable, however, we already know that for the low income group, the value of the predictor, that's the dummy variable, already takes value of 0. So we could safely supply 0 already. For the interaction, notice here, we are taking a multiplication between the dummy variable and the income, right? That's how the interaction term is generated. When we do this, this term cancels, although we have some coefficient estimates of this interaction term. Same thing happens to the term about the dummy variable, because we are timing one of the factor in the multiplication is 0. So we could simplify this as here. So this tells us that for the low-income group, the intercept is this much, whereas the slope for income is this much. We do the same thing for the high-income group. We notice that after simplification, the intercept for a high-income group is different than that for the regression for the low-income group, whereas that for the slope for income is also different from the slope in low-income group. This shows us clearly that when we build a dummy variable and an interaction, we could let both the intercept and also the slope of a variable to differ between two groups. Any questions so far? All right.
One thing, just one thing, Jerry. So would it be the same if you flipped them? If the high income had a 1 and the the low income had a 1 and the high income had 0?
Mm-hmm. Good question. To see what happens when you do that, I encourage you to run a regression, then see what happens. However, as what we practiced in problem 1 about home prices, right? We already found that the reference, the predicting power, it does the categorical variable. All right, so let's practice before we end our review session. With this model generated, how do you interpret the model? Any volunteers? Did you build the model in a similar way to what I did? Yeah, because in part E, we also need to interpret the model. So how did you plan to do so? Would one of you like to try? How to interpret a model with dummy and interaction terms?
Hey, Jerry. It looks like dummy is if dummy is 1 and not 0, then they will be included into the equation and it will affect the y-intercept, so the height of it, and then the interaction is the one that affects the slope. How did I do?
Not bad. You interpreted it correctly. However, to interpret a model, there are a few, there are things that's, we need to put interpretation in context. That's better to do it that way. What you did was correct, but we could fit that in this context more closely. So to interpret a model like this one I'm showing here, it's useful to show what the dummy and interaction terms means. That's why I illustrated using a regression equation. So when interpreting the model, it's also useful to refer to the regression equation. So by combining all the information about the regression coefficients, we should show that at least 2 things, as we just practiced now. That first, the impact of income on life satisfaction, that's represented by the slope of income, as shown in these 2 simplified regression equations after canceling the terms where the value is already known, it's already 0. So first, we would like to mention that the impact of income on life satisfaction represented by the slope as this one, 0.42, right? Or this one after the calculation for high income group, it's about negative 0.01. They differ between the 2 income groups. And when we supply any qualitative statement, it's always very good to give a quantitative assessment. So for example, by difference, how much do they differ from what to what, right? So that's why I supplied a good template as shown here in week 3 illustration about the regression equation, I think. Okay, this is where it's helpful for not always continuous interpretation. So when we're comparing 2 groups, we could say that when the income group was changed from low income group to high income group, then we say that the effect of income on life satisfaction decreased, right? Because here it's negative in the interaction term. The effect of income decreased from 0.42 to negative 0.01 in every dollar of income. Well, in every $1,000 of income on life satisfaction score. Then we also want to mention the second part. That's where the intercept also differs. So we could say that for the low income group, the life satisfaction that reflects the life satisfaction when income was 0 was about 8, whereas for the high income group, it was about 70. So they differ. Any questions regarding how we interpret a model with interaction? All right. Well, last point we can discuss about the predicting power. Since we already built a model with second order term here, let's see how much benefit we could get by using a square term of income. In contrast with one that does not have this second term, second order term of income. This is the regression model result, where we only have income as the predictor for life satisfaction. That's why I call it simple linear regression. It uses the same technique as what we did last week, right? So we see that compared with the second order polynomial model that has one additional predictor, a simple linear regression model that does not have this second predictor has a lower multiple R squared and also lower multiple R. That's the correlation coefficient between the predicted and observed dependent variable, right? That's what we practiced last time. It also has a lower R squared, also lower adjusted R squared. It means that the error term in the simple linear regression model has a larger variation that's not accounted for in this model. And when we move on to the coefficients, we notice that both the intercept and the coefficient for the income is different between these two models. So that's why if you were asked to build another model where the predictors differ between two models, it's not possible to interpret the effect of that without estimating the model. We always need to re-estimate or refit the model because the coefficients will differ due to having an additional variable or not having an additional variable. That means when estimating a simple linear regression where the second term of, second power or a square of income is not in the model, it's not just that we remove this term, but keep the estimated intercept or the zero order term, the income itself, directly, because these coefficients will change after removing the predictor of the square of income. However, if we compare how much this income squared differ from another model, that's where we use the dummy and interaction. Notice we do not have a squared term of income in this piecewise linear model, right? We find that they are somewhat comparable because the R square and the adjusted R square for both of these two models are about 0.085. So it means that if we allow the slope of the income to differ between the high and low income groups, it essentially captures the pattern observed in the data. This pattern can also be expressed using a squared term of income to show a parabola relationship. That means there could be multiple ways out of the same set of data that we could build a model, and they could share some similar predicting power. Any questions? All right. Great. It seems we had a great night of review session. I hope you do really well in the homework 4 questions. I hope to see you again next week.
Thank you. you said that these notes are on Canvas, right, Jerry?
Yes,
Your
you
notes,
can find it in module and TA session.
TA session. Okay, thank you, Jerry. It was very, very helpful. I appreciate your time.
Bye.
Yes,
Bye.
thank you. Bye.
There's also a Ray. Good night.